All right, so this week we are going to take a look at vectors. It's the last section in Chapter 8. It's also the last section that really covers trig as a real focus. Right? When we finish up Chapter 8, we start Chapter 9. That's the last section of the course, which really doesn't focus as much on learning new concepts with trig. All right, so this will be really the last real heavy trig chapter, I guess, section. All right, first of all, what is a vector? Well, in math, and probably in physics and other sciences as well, the way we define a vector is a quantity that has two parts to it. It has a magnitude and it has a direction. So can anybody think of something, kind of like a real world example, where in order to describe it, or think of how to describe the motion of it, you'd have to know the magnitude of it and the direction of it. Can you think of something that you would use a vector for? Yeah?
Thrown objects such as a ball.
Yeah, if any kind of object that's moving, right? If I just said to you that the object is moving at 20 miles an hour, that doesn't completely describe its path of motion, right? It just tells you how fast it's going. It doesn't tell you which way it's going. So in that case, the magnitude is how fast the object is going, and the direction is which way it's going. Okay, so any kind of velocities, we describe them as a vector. And there's one other thing we're going to focus on that you use vectors for. Anybody know the other thing? You might have done this more in physics. Yeah?
Acceleration.
So we don't talk too much about acceleration. Thank you. I know with acceleration, that's the time rate of change of velocity, how quick the velocity is changing, and velocity is described as a vector. So I'm thinking of something different. Something else you can describe. Yeah?
What was the question again?
Something else we can describe, you probably do a lot with it in physics as a vector, besides speeds. Yep?
Force.
Forces, yes. So forces can also be described as vectors. Because when you exert a force on an object, it's not only how hard you're pushing on the object, but which way you're pushing on it. There's a difference between pushing down on something or pulling up on it. So when we want to represent a vector visually, we can draw it as an arrow. Now, I'd say the best use for drawing out a vector is in a word problem, okay? Because then you can actually see it. You can break it down. A lot of times we break it into right triangles. And then from there, we can analyze whatever they want us to figure out what's going on. We'll do a lot visually at first, because I think the visual does help you to understand what's happening. But drawing isn't always the fastest way to do the problem. Okay? But it is a good way to try to understand what's happening. So if you think of, let's just kind of look at velocity vectors for a second. So here's a map of flights, okay, all different flights in the area. And each one of these flights has a magnitude and it has a direction. And that's basically how they can track where it is and hopefully keep all the flights safe distance apart. Right? So if I click on any flight, let's click on this one. All right, so this one's going from en route to New York. So it's Boston to New York. So if you look over on the side, it's going to say, let's see where it says it, speed. Okay, well there's the magnitude of it. So right now it's 334 miles an hour. And the direction, well, they describe the direction as a route. Okay? The direction isn't always constant. Okay? At one point, the plane was traveling east, and then south, and then southwest, and then northwest. So the direction is changing a little bit for whatever reason. When we look at directions, most of the time we're going to keep the direction the same in the problem. because the more times the direction changes, the more complicated it gets. So if you actually click on the direction, you can see the different headings. Okay? So those different headings, those are compass headings, and that tells you the direction that it was traveling. Right? What's a little different about compass headings is when we draw our like unit circle, where do we put 0 degrees? When we're graphing something like a unit circle or anything like that.
Positive x-axis.
Yeah, we put 0 degrees on the positive x-axis. So that's how we do it. But when you're using a compass, 0 degrees is at north.
Yeah.
Right? So if you saw a heading of, somewhere around 180, for us, 180 is usually to the left, but on a compass, 180 is south. Right? So I remember when I clicked on the route, I saw the plane was heading south at one point. So there's probably some headings of somewhere around like 160 to 200, somewhere in there. Yeah, 205, 212. Those are all like a south to southwest kind of direction. Yep. All right. So that's an example of where you can use vectors. Planes. Forces, I don't have a website I can show you for that one, but we'll do a word problem later on with that. All right, so if you're going to use an arrow to represent a vector, well, an arrow naturally has an arrowhead on it, so it points in a certain direction. Okay, so the way that the arrow points tells us direction. The longer we make the arrow, the bigger the magnitude. So I drew a vector like this and a vector like that. Each one of those vectors has the same direction. What would be different about them is the magnitude. Okay, and what does the magnitude mean? Well, you've got to look at the context of the problem. If these were two objects that were traveling, the top arrow is traveling faster. Okay, if these were two forces being exerted on an object, the top arrow is pushing on the object harder. Okay, so when we draw a vector as an arrow, it has 2 points to it. It has an initial point and a terminal point. So a vector is not, it doesn't go on forever. Okay? The arrow has a stopping point. So it's kind of like a ray from geometry, but we know that a ray, think of it as like a beam in a flashlight. Right? It just keeps going. It doesn't stop. This is an arrow that stops. If it didn't stop, that would represent something like going infinitely fast, or something pushing infinitely hard. You can't have that. Okay, so all vectors have an initial point and a terminal point. And there are different ways that we can symbolize this vector. You can use a notation from geometry, like that. Okay, that would be, you could use that to represent the vector, or we can also just represent it as a single letter. Now, we already use single letters for something else. Okay, those are variables. So we have to make this different somehow. So if you want to describe a vector with a single letter, there's one of two things you can do to the letter. You can either put an arrow on top of the letter, and that means it's a vector, or the way that I'm going to do it most of the time is make the letter bold. So a bold letter is a pretty common way to indicate that it is a vector. And I think if you look at your book, that's the notation that they're going to use most of the time, bold letter. Now, there are certain letters that We have to be careful if we use them. I, J, and K are very special letters in this section. So if you want to name a vector, don't pick an I, a J, or a K. You can pick any other letter besides those. What might be another letter that's not good to use, more because it might look like something else? Yeah?
L.
Yeah, an L, depending on how you make your L, it could look like a 1 or could kind of look like an I. So L is probably not a good one. There's one other one we probably don't want to use.
You kind of decided with I.
Yeah, so I, J, and K, we want to stay away from those three. Yeah.
V?
V? Why not V?
Because it's normally, it's almost always velocity.
Okay, so we're going to be okay with the letter V. In fact, I'm going to use V. V and W I end up using quite a bit because it's what your book uses. But this one I'm thinking of because it might look like something else. Yeah?
An S could look like 5.
Yeah, S's could look like a 5, or a Z could look like a 0. A Z. An O could look like 0. So anything like that, we probably want to be careful, just like you would a variable. But I, J, and K, we don't want to use those specifically because they mean something else. All right. And we'll learn about that tomorrow.
I'm pretty sure Q also means something like that.
Q? Not that I'm aware of. We can use Q. That's okay. Yep. All right. So first thing we want to look at is adding vectors together. Okay. When we take vectors and combine them, whether it's adding, subtracting, or multiplying. Notice I didn't say dividing. So we'll talk about that. But adding, subtracting, or multiplying, you have to understand what is your answer that you're going to get. When you combine vectors together, do you get a new vector as an answer? Or do you get a number? Just a number that's not a vector. Well, in the case of adding, when you combine two vectors together, you get a new vector. And here's one way that you can kind of visualize it. So let's say that we had like two fans, okay, blowing in different directions. Right? We had one fan that was blowing straight up, and then we had another fan that was blowing to the right, and that fan is stronger. How do I know that the wind blowing to the right is stronger than the wind blowing up? Just by the picture. Yeah?
The line's longer.
Yeah, the arrow is longer. Yeah. So if you had, let's say you had like a pool or even like your sink or something. You fill it with water, and you put a little boat in the middle of it, and you aim a fan on it blowing up, and you aim a fan blowing right. What direction is the boat going to go in? Yeah?
A more rightwards direction than up. It's still going to go up a bit.
Yeah, it's basically going to go up and to the right. If we want to see exactly what it's going to do,
We could make a right triangle.
we can do that. So this arrow right here represents the combination of these two acting together. Okay, and I'm going to show you how to do what I did here, and that's how we're going to add vectors to start out. So when you take two different vectors and you combine them together, you get a new vector. The new vector can point in a different direction. In this case, the original one was up. The other original was right. The new one is a combination. It's up and to the right. And as James said, it's more to the right than it is up. But it's still up and to the right. And it has a new length. In this case, the new vector is longer than either of the original ones by themselves. Okay, when the vector gets longer, that's kind of a sign that the two original vectors were working together to create the new one. If the final vector is shorter, then that means the vectors were fighting each other. Right? Like if you had a plane flying at a certain speed and it was flying into the wind would be slowing it down. So we'll talk more about airplanes and airspeed and ground speed and how that works. All right, so let me show you again how to add two vectors. I'll do an example with kind of as a picture, and then I'll write it out. So say you had a vector like that, and a vector like that. And you want to combine those two together to see what's going to happen. Well, you take your first vector, then you take your second vector, and you line them up just like that. So what I'm doing is connecting the terminal point of the first vector to the initial point of the second vector. And then to get the final answer, go from the start point of the first vector to the end point of the second one. And that's the result when you combine these two vectors together. Right, so it's not the fastest way to add two vectors, but it does give you kind of a visual of what it's going to look like. And I think in a word problem, that's pretty helpful. All right, so let's write out what we just did. So to add two vectors visually, you're going to line them up so that the end point of your first vector and the starting point of your second vector are right on top of each other. Once you line them up, you're going to connect the starting point of the first vector to the ending point of the second one. And you can do this with as many vectors as you have. Let's say you had this one, that one, and that one. And you wanted to know what's going to happen when you combine all of those together. Well, you just have to line them all up. Just like that. We'll worry if the order matters or not. We'll talk about that in a minute. But you just connect them all together. When you connect them all, there should be like a one-way flow of, think of it as like water flowing. Right? It should always flow in one direction. If you end up with something like this, that's wrong. It's almost like now there's like a collision there. It's not following a nice path. Okay. So we're going to talk about it, but do you think the order that you connect the vectors in is going to matter?
Yes.
You do? Okay. Well, we'll see if it does in a little bit. Okay. So any questions on that? Okay. So let's try adding a few things visually, and we'll see if the order makes a difference. So this first one says to add V plus W. So first thing you'll do is take V plus U. Put that on your grid. And then you're going to put W on the end of it. Okay, generally, when you are adding vectors, you do want to use graph paper. You don't really need an X and a Y axis. You just need some kind of grid in the background, especially if you want to measure distances after, because that's part of what we're eventually going to do. When I combine these two vectors together, I'm going to want to know for the new vector what angle is the new vector pointing at. So I'm going to have to figure that out, and I'm going to want to figure out how long that new vector is. We're not doing that yet. But that's the answer, just like that. So that is vector V plus W. Any question on that one? So the final answer is an image. It's a picture. Now, what do you think a downside could be? Besides, it is slower to draw it out. And you need a ruler and graph paper to make it accurate. But what else do you think would be a downside of drawing it visually? What could happen? Yeah.
You can make mistakes with where the initial and terminal points are
Okay, so let's assume though you don't. You line it up right. You got to make sure you position it in the right spot. So assuming even if you do everything correct, what could still happen? And I avoided it here by where I placed my initial vector. But if I had put the initial vector in a not so good spot, what could have happened? Well, let's pretend that these vectors, let's say like I had a vector like this. Just put this over here. Let's say that's my original vector, and this is one of my other original vectors. And I want to add them together. So what's going to happen when I try to add them together now? Yeah?
You would go off the paper.
I'm going to go off the paper. All right, so if my vectors are really big, and you're trying to add them visually, you're going to need a really big piece of graph paper. Okay, so that is one downside to doing it visually. And we'll see that this can very easily happen when we start scaling vectors. Scaling means you make it longer or shorter. Well, if you make it really long, it's going to go off the paper. All right, so then you have to figure out how to scale your axes, or you got to do something different. All right, let's try this one. I'm going to add V and W together. Any thoughts what's going to happen on this one? Yeah?
They're going to cancel each other out if they're equal.
Yeah. Well, what do you mean they're equal? What's equal about them?
They're roughly the same, aren't they?
Okay, so they have the same
Force.
I'm thinking more general. That would be like maybe specifically if this was about force. It could be the same force or the same speed, but in general they have the same, yeah.
Same magnitude, opposite directions.
Yeah, they have the same magnitude, whatever magnitude means in this problem. But they do have opposite directions. Okay? So think about the two steps. You're supposed to line up the ending point of V with the starting point of W. So you have to line those green dots up. Once you line them up, you're supposed to connect the starting point of V to the ending point of W. So you're supposed to line the green dots up, and then once you do that, connect the blue dots, starting at V and going to W. But if I line the green dots up, then the blue dots also line up. Well, we just added two vectors together. So what did we say earlier? What do you always get when you add vectors together? Yeah?
A third line.
No, not a third line. Yeah?
A new vector.
A new vector. So you have to write your answer to this as a vector. Visually, there's nothing you can draw. But what we can do is this. That's called the zero vector. You can do that, or you can do that. That's not the number 0. Because when you add two vectors together, you have to get a vector. This vector is the only vector that doesn't have a direction to it. Think about it. It has no length. So it's not pointing in any direction. So the 0 vector is kind of it's a special case. It has no length, and it has no direction. But it is how you represent the case where two vectors completely cancel each other out. Okay, a real-world kind of example of that, you might think of like a tug of war, right? If two teams are pulling, it's not that there's no force. There's a lot of force in that rope. If you cut the rope, everybody would probably fall. So there's a lot of force happening. It's just that the amount of force pulling one way and the amount of force pulling the other way are canceling each other out. And that's called equilibrium. Everything is balanced. And we're gonna do a problem probably tomorrow involving equilibrium. Any question on All right, so I asked you earlier if you thought the order mattered when you add two vectors up. It turns out it doesn't. Whether you add 2 vectors or 20 vectors, you can stack them together in any order you want, and you will get the same answer. So when you're adding vectors together, the commutative property and the associative property both work. Okay, I'm going to show you the commutative first. And I'm going to do this purely as a visual. So commutative property means you can change the order that you add 2 things in, and you still get the same result. Okay, so here's my 2 vectors. First, I'm going to do v plus w. To do v plus w, that means you take v and you put w on the end of it. Then draw from where you started to where you finished. And that is v plus w. Now I'm going to reverse it. I'm going to do w plus v. To do that, I'm going to take w and then put v on the end of it. And draw your arrow one more time. Now, I did not use a grid, so it might not be perfect. But that's w plus v. If you line the 2 up, well, that's pretty close. All right? Not bad. So that's showing that the 2 vectors, our addition between 2 vectors is commutative. Right? And again, that works even if you stack 4 or 5 vectors together. The order you stack them up in doesn't matter. You just always have to connect them, what they call like head to tail, right? Initial to terminal. That's how they have to connect. All right, so that's commutative. Associative does not have to do with the order. It has to do with how you group them. Okay, so remember, when you think of associative it has the word associate in it. Associate, how do you associate? Associate is in a group. Right? Who do you associate with? It's kind of like who's your group that you talk with, right? So parentheses are how we group in math. So notice the order is exactly the same on each side. ABC, ABC. What we're looking at, though, is what's grouped. What do we do first? And it turns out it's not going to matter. Okay, this has a 3rd vector, because that's the only way to demonstrate associative. Because I'm using a 3rd vector and I'm drawing by hand, it gives me one more chance to make my margin of error a little bit worse. But just try to do it best we can. All right, so the first way, it says to take A and B and add them up. So there's A, there's B, and if that's too close to horizontal, it's going to mess me up because I can't. Yeah, it just kind of jumps. Yeah, so what I'm going to do is I just got to fix that a little bit. Let's do that. Hopefully that's better. Okay, so now let's take A and B, add them up. So move that off to the side. So that's A plus B. And now it says to add C onto the end. So I'm going to take C, I'm going to put it on the end, and now I'm going to connect my start to my finish. Just like that. Even the arrowhead's kind of big here, so there's a little bit of room for error. Okay, so that is the one you get doing it the left-hand way. Put that back, and we're done with that. Any questions how I added the 3 up, doing A plus B first, and then C? Okay, now the right-hand way. It says to take B and add C onto the end of it. Here's B. And now I'm going to put C on the end of it. Okay, so I'm going to do that first. Okay, so make my arrow. All right, so there's B plus C. And now I'm going to take A, and I'm going to add what I just did on the end of it. So here's A. Put what I just did right on the end. Draw my arrow. And that's what I get doing it the way that's on the right. Now let's line them up and see how close. Not bad. A little bit off because, again, I'm doing it by hand, but they're pretty close. Now, that's not really a proof. That's more of a specific example showing you it came out the same each way, but that works all of the time. Any questions on that one? Now, just because commutative and associative work doesn't mean we can assume every property we know works. Okay, when we get into multiplication, does distributive work? Well, we'll see. Can you do commutative property with multiplication? Well, with numbers you can. 5 times 2, 2 times 5 is the same thing. Can you do it with vectors? Vector v times w, is that the same as w times v? Whether that works, so the answer is it depends. So we'll talk more about that on Thursday. Okay, what would be the difference between those two vectors? Vector v and vector negative v. What would be different? What would be the same? Yep.
The magnitude is the same, but the direction is different.
Right. The magnitude is the same. The difference is the direction they point. Can you be more specific about the relationship between the directions?
They're opposites of each other.
They're opposites, yeah. So it's like rotated. It's like one vector is rotated 180 degrees. But they have the same magnitude. If you were to take the first vector, whoops, and the second vector and add them up, what's the result? Yeah?
0.
How would you write that? Yeah?
A 0 that's bold or
Right. If you add those two vectors together, the answer is technically the 0 vector, not the 0 number. So you'd have to add them up and make the 0 bold, or put an arrow on top of it to indicate the 0 vector. So that technically is wrong. When you add these two vectors together, you should have that arrow on top. If they use arrows in the problem, I would use arrows in your answer. If they make things bold, then you could make things bold as well. Just do it however they do it. All right. Subtracting two vectors. Well, we're going to think of subtraction the same way we did addition. Let's say with numbers, you had to do 3 minus 2. But you don't, somebody who you're explaining this to doesn't understand subtraction, but they understand addition. They understand everything about addition. How could you explain a subtraction problem in terms of an addition problem? Yeah?
In this case, it would be 3 plus negative 2.
Right. You could think of it as 3 plus negative 2. Can you be more specific about how does that relate to that?
It's just in the opposite direction from the origin or 0.
Right. If you think about, like a number on a number line, it goes in the opposite direction. Well, we can do the same thing with vectors. If we have to subtract two vectors, we're not going to think of it as subtraction. We're going to think of it as addition of the opposite. And the opposite as a vector means it points the other way. So to subtract two vectors, take your second vector, find the opposite of it, and then add that onto the end. So that gives us a very, very simple way to do subtraction using what we already know about addition. Rotate the second vector 180 and add it onto the end of your first vector. As far as operations with vectors, these are the only two we're going to do today that has a vector for the first part and a vector for the second part. We're not going to look at multiplying a vector times a vector today. Okay, that'll be on Wednesday and Thursday. And that's because there's a little bit more to multiplying a vector and a vector together. All right, so let's figure this one out. V minus W. Instead of thinking of that as V minus W, how are we going to think of it? Yeah?
V plus negative W.
All right, we're going to think of it as V plus the opposite of W. Okay, so that's the first thing you have to find. Find the opposite of W. Well, easy way to find the opposite of something, if you have a tool that can rotate at 180, that'll do it. I don't. What's the other way you can find the opposite of something? It's another. You can't do it as a single transformation, but there's two things you can do in geometry, and it'll automatically make it point the other way. Yep.
Flip over the X and Y axis.
Yep. If you do a horizontal reflection and a vertical reflection, that's exactly the same as a 180 rotation. All right, so that's negative W. Now take V and add negative W onto it. There's V, there's negative W, and what you're really doing is V minus W. Okay, if it's too horizontal, no, that one's okay. Put that up there. All right. Any question on how we got V minus W? Okay, so that's subtracting two vectors. So next thing we're going to look at is what's called scalar multiplication. Now, I just said to you we're not going to look at multiplication until Wednesday or Thursday. Well, I said a vector times a vector. Scalar multiplication is not a vector times a vector. It's a vector times a regular number. When you multiply a vector times a number, like that, 3V, that number in front is called a scalar. And a scalar does exactly what it sounds like. It takes the vector and it scales it. When you scale something, you can make it larger, right? Like if you're making a scale model of an atom, maybe you probably make it larger. I don't think you're going to make your scale model smaller. So if you're doing that, it would be larger. Or if you're making a scale model of a house, you'd probably make that as a smaller scale. Right? So you can scale something smaller or larger. Regardless as if you scale smaller or larger, the result that you get when you scale a vector is another vector. There's actually three things that can happen depending on what kind of number you put in front. I already said two of them. Yep.
Couldn't you go negative?
So what would happen if the number was a negative?
It would invert it. Or it would flip 180.
Yeah, it would rotate at 180. It would point the opposite direction. So that's the third thing that can happen. So when you scale a vector, it can get longer, it can get shorter, or it can rotate 180 degrees. That's all that can happen. I guess if you were thinking, well, what if I had the zero vector and I started with that? Well,
Just scaled it to 0.
yeah, if you have the zero vector and you scale it, it stays the same. So I guess staying the same length would be a fourth option. You could also just do that if you put like a 1 in front of a vector, that doesn't scale it. But I'm talking about things that actually change it. Longer, shorter, rotate 180 degrees. And scaling is one that if you are going to draw it, you can quickly go off the graph, especially if you scale something like 40 or 50 times bigger. So any question on scalar multiplication? It is not a vector times a vector. Okay, it's a number times a vector. So here's some examples of scalar multiplication. First one they want me to find is 2v. How could I find 2v on the smartboard exact? I don't want to measure. I don't want to get out a ruler or anything like that. Yep.
Couldn't you just duplicate it and add it onto that point?
Yeah. Whenever you're finding a whole number multiple, that's easy. You just have to copy it that many times. So that's the setup. And now the actual answer is connect where you started to where you finished. So did the direction change? No, the direction is exactly the same. What did happen is the magnitude doubled. What does that mean? Maybe the object is going twice as fast, or the force being exerted is twice as hard. Now, 1/2 v, I don't really have a way to do that exact. Okay? It would be half as long, pointing in the same direction. So for that one, I'm just going to estimate whatever. So any question on those two? Let's try this one. So now they want -1v and -1/3 v. Okay. How are we going to get -1v? Yeah.
Rotate 180 degrees.
Yeah. And for that, I know I could do it exact, but I could just trace it like that. So it points in the opposite direction, but the length is preserved, stayed the same. How about -1/3 v? How am I going to get that one? Yeah.
First rotate it by 180 degrees or
Okay, so we can rotate it, and we've got that from the last problem.
yeah, and then just take 1/3 of it.
Yeah, I just got to take 1/3 of it, so I don't know, just estimate maybe that's 1/3. Again, on graph paper, I could easily figure that out. Because if you're on graph paper, and let's say something like that, that looks like it's over 1, 2, 3, 4, 5, 7, over 7. Well, if you wanted to make that 1/3 as long, instead of going to the right 7, go to the right 7/3. And instead of going up 4, go up 4/3. And that would land you exactly at the terminal point. That's 1/3 as long.
For an exact, on the smartboard, for an exact shrink, couldn't you make a reciprocal version of the original subscale? So, for example, you take the original and make it 3 times longer, and you just scale the entire down to the original and just delete 2 extra lines.
Oh, if the original was 3 times as long.
And then you scale the
yeah.
line down to the 3 separate lines that are the original.
Yeah, I guess you could do something like that, yeah.
Yeah, just
Yeah.
be full.
Okay, any question on that one? Okay, so that's a scalar product. Now let's look at one that's combining a scalar product with addition and subtraction. Let's just do, I don't know, let's just do the first one. 2v plus 3w. So I'm not going to do the second one. So to do this, it requires a little bit of planning ahead because I have to look at the directions V and W are going to go in, and I want to make sure I start on the opposite side of the graph. So what direction does V go in? Yeah?
It goes roughly 45 degrees. If we're on the compass.
Okay, so if we're thinking of it, it's kind of like a 45-degree angle, so it's up
Yeah.
and to the right. And how about W?
315.
Yeah, so that's down and to the right. So I definitely want to start to the left. Okay, give myself enough space to move to the right. And we're going to be going up and to the right, down and to the right, so we probably want to start maybe kind of in the middle. All right, so we need 3 copies of, oh, we didn't need that many.
Well, we still need one as a reference.
Yeah, I'm going to use the original. So we've got 2 copies of V, and we need 3 copies of W. Okay, so I would start with V maybe right about there. So that represents 2V, and then we're going to put 3W on the end. And if I planned well, hopefully I don't go off the graph, which I did not. Okay, so 2V plus 3W. And then connect where you started to the finish. And that is the final answer. B plus 3W. All right. Any question on that? Combining a scalar product with addition. All right. So up until now, everything we've done has been visual. But in a minute, we're going to start to get away from representing things as arrows. Okay, so I'm going to show you a few more symbols we can use to represent things without actually drawing it. So one symbol we can use if you want to represent the magnitude is these double bars around the letter. Okay, when you put double bars around a vector, it stands for magnitude. Okay, and how you find the magnitude of something? Well, when I drew this picture earlier, it might have given you a little bit of an idea. I'll just leave it at that for now. But we'll talk more tomorrow about how you would get the length with a magnitude of a vector. It's going to involve doing something we've done before. So what would be the difference between these two? The magnitude of vector v and the magnitude of the vector negative v. What would be the difference, yeah?
They're the same.
They're the same. These two answers are exactly the same because when you are finding magnitude, the magnitude is always positive. So whether you measure the length from here to here or from there to there, those two vectors have exactly the same magnitude. What is different is the direction that they point. But the magnitudes themselves are the same. All right. When we talked about the circle, right, we did start a lot of trig on a circle that had a radius of 1. Does anybody remember what we called that circle? Yeah.
Unit circle?
Unit circle. Okay, well, that word's going to come back up here. It's not going to have to do with a radius being equal to 1. It's going to have to do with a magnitude equaling 1. Anybody have a guess what you would call a vector if its magnitude is exactly 1? Yep. It's called a unit vector. There are 3 special vectors that are unit vectors we're going to study tomorrow. Actually, we're only going to study 2 of them tomorrow. And their names are I, J, and K. That's why when you are naming a vector, unless you know you're talking about one of those vectors in particular, you never pick I, J, and K as a random letter for a vector. So a unit vector is a vector with a magnitude of 1. If the magnitude is not 1, it's not a unit vector. All right, so if we're going to start doing more with vectors, drawing them every time, that's going to be time consuming. I think drawing is good when you got a word problem and you have to kind of visualize what's going to happen. But if I just want to take and figure out something like this, I don't really want to have to stack 2 V's together and 3 W's together. I mean, what if this was like 21V and 35W? Right? Am I really going to stack together 50-something vectors? That's not very efficient. So there are 2 other ways we can represent vectors besides pictures. The first way, and the only way we'll talk about today, is what our book refers to as an algebraic vector. Okay, essentially, it looks like that. That's a vector. Okay, it looks kind of like a coordinate, but there's an important difference. Yep.
Can you scroll up?
Yep.
And you just continue what you know.
The big difference is it's 2 numbers separated with a comma, but there's brackets, these angle brackets, instead of parentheses. And the numbers inside are not locations. It's not like a coordinate where the first number tells you like a left and a right, and the second number tells you an up and a down, and then you put a dot on that number. We're not putting a dot anywhere. Both of these numbers are lengths. Specifically, they're the lengths of the horizontal and the vertical components of the vector. So if I were to go back to that diagram I drew a minute ago, right here, if I wanted to write this vector, not as a picture, but as an algebraic vector, it would be 7, 4. That's the vector 7, 4. The 7 tells you from an initial point the length you need to go to the right, and then it tells you the length you need to go up. So the 7 and the 4 are really the lengths of 2 sides in a triangle. The horizontal length, that's called the horizontal component of the vector. And the vertical length is called the vertical component of the vector. So think of the A and the B as lengths from an initial point to a terminal point. But there's something that this notation doesn't tell you. If you look at that vector 2, 3, this is the length from an initial point to the terminal point horizontally. That's the length from the initial point to the terminal point vertically. But anybody see what that notation doesn't tell me? Yeah?
The magnitude.
Okay, it doesn't tell me the magnitude directly. We'll talk about tomorrow how we could figure it out, though. But there's something else it doesn't tell me. Yeah? Well, it tells me to start somewhere, go 2 units right, 3 units up. So because it's telling me right and up, I kind of know the direction. Yeah?
Not like where it is on the graph.
Yeah, it doesn't tell me where to start. It just says to go 2 units right, 3 units up. So if you wanted to draw the vector 2, 3, you could put it right there. That is the vector 2, 3. Okay, you could put this vector anywhere you want. Doesn't matter if I move that. To put these vectors anywhere. These are all the vectors 2, 3. You can start anywhere you want. You can stop anywhere you want, as long as you always go 2 units right and 3 units up. Now, there is a common place that we usually do start from. Does anybody have a guess which point would be the most common place to start your vector from? Yeah? Yeah, the origin. So what this notation doesn't tell you is where to position the vector. If you start at the origin, that is called a position vector. So if a vector has its initial point at the origin, that is a position vector. So what I want to do is I want to get rid of all of these. And let's just focus on one of them. And I want to see how could I convert that into a position vector. Now, I know I can just look at it and say, oh, it's 2 units right, 3 units up. So start at the origin, 2 units right, 3 units up. I'm more interested in how I could do it numerically without actually sketching anything or measuring distances. And what they would give you in this kind of problem is coordinates. What does it look like the coordinate is for the initial point? Yeah?
4, 4.
Yeah, looks like the initial point is at 4, 4. And how about the terminal point? Where's my terminal point? Yeah.
7. No, wait, no. 6, 7.
6, 7. Okay, so I got my initial, and I got my terminal. We already know the answer is 2, 3. That's the vector that it would have to go 2 units right and 3 units up. Does anybody see what I can do with these coordinates to get the answer 2, 3? Something I can do, yeah?
Did you subtract the top set of coordinates from the bottom set?
So tell me how would you do your calculation?
I would take the higher x value and subtract the lower x value, take the higher y value and subtract the lower y value.
Okay, that would work for this one, but we have to describe it a little bit more differently in general. But yes, what you said would work for this problem. Yeah.
Do you subtract terminal x's and terminal y's from the initial x's and initial y's?
Subtract terminal from initial?
Flip that.
Flip that. Subtract initial from terminal. So you want to do subtract, is that the way you meant?
Yeah.
Okay. Terminal minus initial, yeah. If you do that, and I'll write that down nicer in a minute, with your coordinates, you will get this. 6 minus 4 gives you 2. 7 minus 4 gives you 3. And yes, this time the terminal coordinates are bigger than the initial, but that doesn't always have to happen. Okay. Going back here. So how do you find a position vector if all you know is the starting point and the stopping point? Well, first thing is, how are they going to identify which point is which? They might say initial and give you a coordinate, terminal, give you a coordinate. If they don't, and they just say P1 and P2, P1 is always the initial. P2 is always the terminal. So think of 1 comes before 2. 1 is the start, 2 is the end. That's how you find your position vector. Terminal minus initial for the x's. Terminal minus initial for the y's.
Do I need to sign out?
No, you're okay. So any question on that? For you? Oh, you're good. Yep. All right. Well, let's take a look at how we would figure out the vector for a point I'm going to give you in a second. Okay, I'll keep that up. And let's do that. Okay, so find the position vector. P1, P2. Okay, based on the notation, you need to know which one is the initial. Okay, and the initial there is which one? Yep.
P1.
P1. Yep. Okay, let's set it up. To find the horizontal component of my vector, what am I going to put in the first part of that for my calculation? Yeah.
4 minus -1.
4 minus -1. Terminal minus initial. So 4 minus -1. And then how about in the last part? Cole.
6 minus 2.
Yep, 6 minus 2. Simplify it. And that is the vector in algebraic, well, what our book calls algebraic notation, 5, 4. So we'd start at the origin, go 5 units right, 4 units up. That's what they're looking for, position vector. Okay, any question on that? All right, so that's the first part of vectors. This is probably the most visual heavy day. Most of what we do, with the exception of word problems, is all going to be numeric now. Okay, we're going to learn adding, subtracting, all that, but without a sketch. All right, so the homework, you noticed it does look a little bit different because it's from a different book. But I showed you it's section 5.4. 1 through 10, that's all 14 to 22 even. And then on 26 to 32, they ask you to do 2 things. We haven't learned the second thing yet. So all I want you to do on 26 to 32 is find the position vector.